All right, good morning. Happy Wednesday. Today's lesson is on arc length of a parametric curve. So yesterday we did arc length of a rectangular curve, which I don't have on here. But this is when it's in a parametric system, so it's parametrically defined. All right, so we can discover this equation. So here's your formula down here that you need to make sure you memorize. We can discover it from our arc length of a rectangular system. So from yesterday, the arc length of a rectangular function was the integral from x to x of the square root of 1 plus the derivative of x squared. So from that, we can move into a parametric system by using the same equation, but our derivative, so dy dx, we're trying to get this into terms of t. So dy dx is dy dt over dx dt. Okay, so the next thing I did on the inside of this radical is I distributed a square. So I squared the numerator and the denominator, and then I got a common denominator. So the 1 over here, so the 1 turned into dx dt squared over dx dt squared. That says dx. Let me fix that. It should be dt squared. All right, good. Now the goal down here is to not have this denominator, and it's to change and to be in terms of t. So the way we accomplish that is we multiply this thing by 1. But by quote-unquote 1, we call that dt dt. So multiplying by dt dt is allowed because dt dt is just 1. I'm going to go ahead and put it right here, this part of the dt. Okay, next thing I want to do is I need to move the dx dt into the radical. So I'm going to square it and take a square root. So that's still a net change of nothing because I've squared and square rooted. But the benefit of that is that allows me to multiply this into one big radical instead of two. All right, so now the dx dt in the numerator and the dx dt in the denominator are going to divide each other out, and they just become 1. And then that's how we get to my final answer. So the formula for the equation of arc length in a parametric system is the integral of the square root of dx dt squared plus dy dt squared. So rectangular system is the square root of 1 plus dx dt squared, and then parametric, it's the square root of dx dt squared plus dy dt squared. All right, so these aren't too bad. This is really, if you know the equation and you can take a derivative and a definite integral, these are some simple questions. Now it's a good chance to review these skills, make sure we can still have them and we can do them. So number 1, position is defined parametrically. Find the distance the particle travels from time 1 to time 2. So it's the square root, and then this is dx dt, and this is dy dt, and I'm squaring them both. Then it's just algebra, so I squared both things. Don't forget to square the 2. I've FOILed this out. Okay, I combine like terms, so 4t squared minus 2t squared is 2t squared. Here's the most important step in this whole problem. This is a perfect trinomial. It can be unfoiled, if you will, but you can rewrite that as t squared plus t quantity squared, which is so awesome because the square root of the square go away. And now once you get to here, this becomes a really, really basic integral for you to solve. Take the antiderivative, make sure you can get all the way to the end. This will be a multiple choice question on the FRQ on the AP test, and the answer would be 10/3. So there won't be, you have to be able to do the fractions and things all the way to the very end. All right, example 2, they're trying to trick you here by defining x and y as integrals. So they're trying to just scare you, but we're not going to be scared by that. It's not a big deal. So remember, so find the length of the arc. So what I need is dx dt. Well, the derivative of an integral, all you got to do is replace t and chain rule it. So that's where this comes from. So if I'm taking the derivative of the integral, second fundamental theorem of calculus, you just plug in that upper variable and multiply by the derivative of it. So plug in t and multiply by 1. Same thing for dy dt. Plug in t to everywhere the variable is, and then multiply by the derivative of t. So that's where I got my derivatives. There and there. All right, next thing, there's one more little added thought component to this. So it says, find the length of the curve from the origin to the nearest vertical tangent. So two things you got to be able to think about there. First off, the origin. So I actually did the origin over down here. So the origin means not necessarily where t equals 0. Origin means you're on the xy plane at 0, 0. So if I want this to be the origin, I need my x value and my y value to both be 0. Well, now you gotta, this is a little extra thinking. How am I gonna make a definite integral 0? Well, the only way is if the limit, not the only way, but the easiest way is if the upper and lower limits are the same here and here. Because that means you don't have any width. And if you don't have any width in your area, then you don't have any area at all. So the way you find the origin is you make x and y 0, and the way I accomplish x and y to be 0 is t equals 1. So that's my lower integral limit. Now, the next thing it says is where there's a vertical tangent. Vertical tangent means that dx dt equals 0. Because if I'm vertically tangent, I'm straight up and down. Two ways to think about that means that your slope is undefined, which would be the denominator, which is dx dt, or that means you don't have any change in x, and dx literally means change in x over time. So I set dx dt equal to 0, so cosine of t equals 0, so t equals pi over 2. So that's how I get my setup here. Now it's just a matter of some really good algebra. So you square the top and the bottom. So you get cosine squared plus sine squared over t squared. Now cosine squared plus sine squared is, cosine squared plus sine squared, that's just 1. And then the square root of 1 is 1. And then the square root of t squared is just t. Now I got the antiderivative of 1 over t is the natural log of t. Plug in pi over 2, plug in 1. Remember that, yeah, there is a little more to this, but the natural log of 1 is just 0, so we don't have to write that. Really, really good question. Go back and rewrite that. Make sure you understand everything about it. 3, here's a softball. These will absolutely show up multiple choice. Set up, but do not evaluate. Meaning all you got to do is write down your limits. I wrote a t there for some reason. 2. 4 is too much arithmetic. We're not going to worry about 4 outside of class. It's not important right now, really. Example 4b, 3. So this is a cool image. It says a circle of radius 1 rolls around the circumference of a larger circle of radius 4. The figure traced out by the point on the circumference of the smaller circle is called an epicycloid, given by this function. This is a cool image. I would graph it in my T84 and watch it, kind of sketch it out. You can get this by, one way people describe this is like if you have a quarter and a dime and you're spinning the dime, so the quarter is stationary, and then your dime is rolling around the outside. Well, if you like traced one dot on the edge of that dime, this red curve is what you would get here. That's your epicycloid. So to find the arc length of the red curve, we take the derivative of x and the derivative of y. Sometimes I like to do that kind of out to the side, not in the middle of my integral. Be very careful. Number one mistake on this problem is right there, not chain ruling. So the derivative of sine 5t, you got 5 cosine 5t, and the derivative of cosine is the same way. So don't forget the chain rule there. So then I just do the integral from 0 to 2 pi, the square root of dx dt squared plus 2y dt squared. Plug in your calculator and equals 40. you actually can evaluate this by hand. It takes a while. You got to use some trig identities. It's pretty tricky. We would have done it in class. It was kind of cool, but it's a whole lot of work and not expected of you. All right, example 4, and the last one. I think there's one very similar to this on your web assignment tonight too. Verify the equation of circumference of a circle. So where did the circumference equation come from? You all know that C equals 2 pi r, which is very nice. But you can prove it here by using a general parametric of a circle. So remember, first off, this is good recollection from last Friday. This is a general parametric of a circle. So remember, A is your radius, and they have to be the same. If A is different from the other A, that means this would be an ellipse. All right, so it's general, meaning I'm not using a specific radius, so don't do it for like a 4. You want it to be A, so A is just a letter. So I set it up. I got my integral derivative of x squared plus derivative of y squared. I'm distributing the square here to both things. I then factored out the a squared from both terms, so a squared sine squared plus a squared cosine squared. I took the a squared out. Sine squared plus cosine squared is just 1, so this is just the square root of a squared, which is just plain old a. Antiderivative of a is a theta, because my variable is theta. Plug in for theta, you get the circumference equals 2 pi a. And remember, a is the radius, so the circumference equals 2 pi r. All right, that's it. You got a web assigned tonight over parametric arc length. They're also in your Google Drive, some practice multiple choice questions. Now, this is the whole chapter's worth. We've only done parametrics. So you're only responsible for the ones that are parametrics. 1, 2, 3, 4, 7, and 13. We will do the rest of them as we get to them. There's a blank copy as well. 1, 2, 3, 4, 7, and 13.